Okay, let's getting right on to the next presentation. I'd like to introduce Jerome Dapore. He is a veteran of the industrial measurement and controls industry using laser, ultrasonic, magnetic, and other technologies to improve manufacturing processes. He has held numerous leadership positions in the product management and engineering during his career. And with that, we'll turn it over to you.
Okay, thanks so much. So today I'm going to talk really about a different type of measurement technology, and it's a tried and true technology. It's based on laser interferometry. But what I'm going to talk about today is not only that as an introduction of that, but also a new implementation of this technology that really adapts the product for wire and cable industry, some metals industries and things like that, where the product itself cannot be guided, it's moving around, it's got vibration, it's bouncing around and things like that. So it's kind of a new take on a tried and true technology. So, and what it has to do with is industrial speed measurements. So, many manufacturing operations can benefit from a very accurate speed and length measurement, where those measurements are quite important. And what I'm talking about today is this type of measurement is accomplished by using a laser Doppler velocimeter. So, and as I mentioned before, this is based on laser interferometry, and it's a laser-based non-contact measurement device. So we don't need to contact the product being measured. And basically what the device does, it measures the velocity of the material presented in front of the velocimeter. In addition to the velocity is integrated over time to calculate length. So not only do you have velocity measurements, but you have length measurements as well. And of course, both of these measurements can be very important in many of the manufacturing applications, which includes wire, cable processes, extruded processes in the metals industries for wire drawing lines, bar, and rod drawing lines, things like that. Okay. So the important processes really that can be served by this technology potentially are as follows. So maybe some of the processes you need to monitor and control the speed of the product. This comes into play in the wire and cable industry. So you want to ensure that you've got your specifications staying uniform, wall thickness, other critical features are able to be controlled, and to monitor and control the speed can be valuable in doing that. Also, total length of a product can be very important, where for material savings and also for meeting customer specifications. So many end customers want a very tight tolerance on the length of the product that you provide them, and they may return your product if you're shorting them material, etc. But of course, you don't want to give them a lot of extra free material as well. So that's why the total length of a particular product is quite important. Other products are important to control at very tight tolerances, the product length. So you may have even a long length that we want to cut it to a very tight tolerance of a few thousandths or something like that. And other applications are just a verification of a specified length that normally the process is under control, but since the customer doesn't, they want to monitor the ability to keep that length within tolerance. They want to have a detection method if something changes in their process and something needs to be adjusted. And also for wire and cable and extruded products, control of printing processes is quite important as well. So if you look at a cable and the printing on it, the specifications as far as that separation distance where the label is between the printing process is generally very tight, so within a few thousandths of an inch, believe it or not. And this technology can help with that, because this technology is very fast in responding to changes in speed, and therefore to control the printer where exactly the printer head prints that marking is updated very quickly. And this is and the problem comes into play where you can't respond quickly because the tension of the line is changing quickly, and you end up with a big variance in that distance between printed text on the cable. So why use a laser Doppler velocimeter? So you're going to get much more accurate measurements using this laser velocimeter. The accuracy is better than 0.03% of the true length of the product that is being presented to the gauge, which is an extremely good accuracy. And a lot of the traditional methods have some difficulties. So traditional methods are going to contain a lot higher error than 0.03%. There's generally a slippage error between the product and a roller that might contain an encoder, or there's slippage between a tachometer. Tachometers are going to require maintenance and periodic calibration. The wheel's going to wear, the wheel's going to slip during fast acceleration and deceleration. You're not going to get the real speed because there's a mass involved in the wheel. So these are all the advantages of a contactless measurement device to measure the velocity and length of material. Also, some products you can't touch the material because you're going to scratch it or mar the surface, something of that nature. And of course, I talked about a little bit about the very fast response to changing velocity is important. And therefore, most mechanical methods of speed measurement are not that good. So what we call our product is it's called LaserSpeed Pro. At the most basic level, it's an encoder replacement. So we can measure the speed, we can provide compatible outputs as people are used to with old technology encoders, but also at its most complex, it's a sophisticated measurement and control device that can be interfaced to customer equipment, PLCs, industrial computers, things like that, to help control a precise production process, such as cut control, elongation of products, and things like that. So we found in our business that there are many critical production applications that really are not possible to operate without the LaserSpeed device. So there's a lot of really high value applications. So laser interferometry uses a principle of superposition to combine waves of the same frequency or wavelength. So there's a resulting pattern that is determined by the phase differences between the two waves. So here I'm going to talk a little bit about the technology because, okay, how does a laser really measure speed? So this is important to get the basic concept down. The concept is very simple, but the technology involved in actually making really accurate measurements is quite difficult. So the implementation is difficult, but the concept is easy to understand. So if we talk about the waves that are in phase, they will undergo constructive interference, and when they're out of phase, they're going to undergo destructive interference. So we start with a single laser beam that's optically split into two basically identical elliptically shaped laser beams. The beams are Gaussian, meaning the optical power is concentrated in the center of the beam, and the two beams are optically set in the gauge to converge in the horizontal axis. So we have two laser beams They're collimated very well. They're at a very precise wavelength and a very stable wavelength. So the two laser beams are going to cross at an angle K. We're going to have constructive and destructive interference. That's going to create what we call a fringe pattern that consists of light and dark stripes, and that's going to be reflected off of the material surface we're trying to measure. Constructive interference, again, occurs where the phases of the light are in phase with one another, and the destructive interference occurs when the phases are not, the laser beams are out of phase. So you can kind of look at it as the picture we see here. You end up with high intensity light and low intensity light strips reflected off of the product. So what we know behind the physics is the fringe distance, D, is a function of the laser wavelength and the beam angle. So we know that we control the laser wavelength, we control the beam angle very well. So that's going to remain constant. So, that's the wavelength and the angle determines what that fringe spacing is. And the velocity is the fringe spacing divided by time. Of course, period is the inverse of frequency, and velocity is the distance divided by time. And also, velocity is integrated to find the length. Now, if we look at this, we've got the laser energy hitting the material surface. That's going to be reflected back to the laser speed probe gauge, and we're going to optically collect this energy. We end up with this resulting electrical waveform that we see something like this. And you see between the wavelengths, we have a certain period of time. We convert the optical energy produced by the fringe pattern into this electrical signal. And since we know the time between these pulses of energy, we can determine the speed of the product that's reflecting the laser energy back to us. So that's really the basics of the technology. So the laser speed, really, there's a lot of processing and processing all the information, but it's really an optical system. The technology is based on an optical system, and the velocity calculation, again, is based on the wavelength of the laser, crossing angle of the laser beams, which produces what we call the Doppler frequency, which is the waveform that's converted into an electrical signal. So the types of applications, again, we have continuous measurement, measuring the total length for the customer order, cut length verification, so to verify critical lengths are cut properly. This will eliminate scrap. If there's a product that doesn't meet specs, it can be set aside. So the customer is always going to produce a product that meets the customer specifications. Cut to length applications. There is programmable and flexible settings that will allow the laser speed product actually to control a saw or a shear or something else that's going to be providing the cut mechanism to the product. And that can be programmed to certain lengths and things of that nature, so that everything on the interfacing of the product is done for flexibility and ease of integration into customer equipment. Printing control applications we talked about before, and then also elongation, like for instance, wire drawing lines, steel rod lines, where we need to control the drawdown process of the steel, so we don't stress the product, and that we can also control the speed of the product and reduce the amount of wear on the equipment on the line. Here's some of the terminology with the laser interferometry. We've got the two laser beams. They're going to converge, and what we call the pass line is where the product is presented in front of the gauge. what we have here is what we call the standoff distance. The standoff distance is the distance between the front of the gauge and where the laser beams are fully converged. So that's the distance, from the gauge to where we can make our measurements, basically. And we do have products anywhere from this distance being 100 millimeters to 3 meters. So depending on the customer application, we can build a gauge, to fit that application as best as possible due to the amount of room the customer has, how close they need to position a gauge for the best measurement performance. Here we also have the depth of field. Of course, we have an angle, and we can only make measurements where the laser beams are overlapped in creating the fringe spacing. So they don't need to be fully overlapped, but wherever we have overlap and we have fringe spacing, we can make measurements. So that's what we call the depth of field. So the important thing about the depth of field, you can measure products that are of different thicknesses without the customer needing to change equipment on the line, things of that nature. Wire and cable applications for marking and printing. This is one such application where we've got an inkjet printer right there. We're measuring the speed, and we are controlling exactly where each of the new printing processes start. Continuous length, same sort of thing. Wire and cable, here we have a wire line where we're measuring continuous length to meet the customer specifications. And here's more of this is a roofing type application where the customer was able to go from 2% accuracy to better than 0.03%. So they improved, reduced scrap, improved productivity, and gave a lot less product away to their customers. This technology is also adapted to the fiber optic applications where fiber optics people are making. Obviously, you have the individual fibers and you have a fiber tube. Well, the difficult thing about fibers in a tube is that, well, as the fiber is being laid, so to speak, the tube is going to bend. So if you think about that, if your fibers bend as well, they're going to get stretched and some of them are going to break. So what's important is that the fiber is a little bit longer length than the tube. So there's excess length. And what we call this whole process in measuring both the individual fiber length and the buffer length is excess fiber length system. So we have two gauges. We connect the gauges together and we look at the differential velocity between the two gauges. And we have a lot of fiber optic customers that are using this and rely on this to make good quality fiber optic cables. Now, getting to the new implementation here, the M series is, there are some difficult applications to get good measurements all the time, which is what we really want, right? So, and we've been very successful and we've sold tens of thousands of gauges in flat applications, but round applications are a little bit more difficult. And we've measured in the wire and cable and extruding industries for many years as well. But there's some applications that it's difficult because the product moves a lot positionally and can't be guided. Also, smooth and shiny products are difficult to measure due to there's not much scatter of the reflected light. So the light energy comes straight back. And we'll talk a little bit of why that's a challenge in some applications. And really the difficulty is keeping the laser spot on the proper area of the product so we get enough energy back to the gauge to make reliable measurements. So here we have an illustration of the challenge. So we've always said, okay, if you're on a circular product, you want to be on the top 20% of the crown of the product. So we get this nice reflected energy back to the gauge. So the laser's coming down, it's reflecting back. There's a little bit of scatter of that laser. And in this case here, we're going to get good measurements all the time. But here on the right, we're off at an angle. The Piper tube moved a little bit, and now the laser is hitting at an angle, and most of the energy is coming off to the side. Well, the gauge is up here, and if the energy is coming off to the side, we're not getting enough energy to actually make good measurements. So in this case, as the Piper tube move back and forth, we get measurements, and sometimes we don't get measurements. So this is the challenge. So we asked ourselves, how do we get better measurements, on these type of products? And really, what we targeted was cable and tube that are not guided, has a bumpy surface, and wire and drawing lines with small diameters. They're not guided and has significant positional movement. Also, we targeted the steel industry, as I mentioned before, but we'll kind of keep the discussion in the cable and tube area. So in this case, I'm going to show a video that we've got a tube. It's very shiny, so we don't have much scattering of light, and the tube is not straight. So in this case, our standard gauge was not successful. And here we just have a linear slide that we test products all the time to see how successful we're going to be. We were not successful with our standard technology of the standard beam profile. And this is because we couldn't keep the laser due to the unstraightness of the product and unguiding of it to get good measurements. But what we did is we adapted a gauge. We used what we're calling the M-series gauge technology. And here we see perfect measurements. The red line is velocity measurements. The blue line is what we call quality factor, meaning if we have 15 quality factor, that means we're making great measurements. If we weren't making great measurements, then this blue line would be jumping around and showing fallout of measurements. We've also had the same sort of situation where a major international construction company uses very small wire. And again, due to the lack of guiding of the wire, we had some measurement dropouts. This is their line. They're basically using a small wire, just running it from a large spool to a small spool. The wire is as small as 15ths of a thousandth in diameter. And so there's not much reflective surface to make measurements. So we needed to go to this M-series technology to be successful. So in these two examples are good examples of how, standard laser velocimeter technology couldn't get the job done. And so what did we do to create successful applications? Well, in the standard gauge, we have a horizontal beam. And in this laser speed M series, we've got a vertical beam. And what we did is we rotated the beam and we expanded it. So we've got a lot larger laser profile. Idea is to keep the laser on the product, even with a lot of product movement. So if you look at a round product here, the red I'm showing, this is the laser beam with the M series technology. But really, the yellow is where we're measuring. This is where we're getting the reflection off the product. And here's our standard gauge. Okay, when the laser is on the center of the product, we get very good measurements. But look at what happens when the product moves. Here with the M-series technology, we're still getting good measurements because the laser's on the center of a product. But in here, if the product moves, in this case, this is where the laser beam needs to be, but the laser is either off of the product or it's at a very steep angle. So we're either going to have no measurements here or we're going to have unreliable measurements. So this rotating and expanding of the laser is solving the problem with the moving product. So the product now can move significantly more and we're still going to get great measurements. Here's a little bit of information from actually a test run of the very first M-series gauge that we produced. And we sent it across the world. This is actually done on a steel rod line where they're elongating the rod. And this is our standard gauge customer is using for many years. our gauge on this line, but you can see here, most of the time we're getting good measurements, but occasionally we have a dropout, and you see our quality factor shows the dropouts as well. So our customer came to us, and it was really kind of a joint project to produce this new gauge, and said, what can we do to improve our measurement capability? Well, we produced this M series gauge with the rotated and expanded beam on the same line, using the same standoff of gauge, and this was our results here. So really perfectly reliable measurements on the same application. So just kind of illustrates what we've been able to do, and this same concept applies to many different applications where there's product movement. So let's talk I know I'm running out of time here quickly, but interfacing of this gauge to customer equipment can be provided with any number of interfaces, pulse outputs, which is compatible with earlier encoder technology, analog outputs, serial data streams via RS-232, 422, Ethernet streaming, Ethernet IP, Profinet, Profibus, Modbus, TCP. So we have all our field buses there as well. And we have a lot of programmable and flexible control inputs and outputs to help the customer to be successful in application. So really, in summary, we have a new product that is to help, that's proven to help keep reliable measurements so that more customers can use this technology in more applications, and know that even when they cannot guide their product and there's a lot of product movement, that those measurements are always going to be successful. So that's really it in a nutshell. It's a new implementation on really a tried and true technology. And that's it for the presentation.
Well, Jerome, you did a great job. I mean, a lot of good information. You have a number of questions, but like you said, we're sort of tight on time. So what we'd like to do is we'll send you the questions, and you can answer them directly to the people, if that's all right with you.
Absolutely perfect. Yep, be happy to.
Because we don't want to shortchange anybody and what they want to learn from you. But that was great. I enjoyed it, and I'm sure everyone else did. I'm going to ask you one question because I feel I should. The first one that came in: do you need an encoder to measure the length of the cable?
So
sure.
With the laser technology?
Yeah, I believe so. It came in early.
So yeah, in this case, we've got reliable velocity measurements. Most of the time, with this technology, we're replacing encoders that are already installed on a line. So we're either providing the velocity or length information via serially streaming, or we're providing a compatible encoder output, quadrature output, just like an encoder would. So it's just the value is that our measurement technology is much superior as far as an encoder would have, due to the lack of mass and the other limitations those other measurement technologies have.
Super. Okay, well, you'll get the rest of the questions, and I'm sure you'll follow up and get back to everyone. But once again, we at the Wire Association thank you for your time and efforts and all the work you put into the presentation. It was very good. Thank you.
Yeah, enjoyed it. Thank you very much.